This video, let's talk about Laplace transform of a derivative. Laplace transform is very useful in electronics because you can use Laplace transform to get rid of the tedious integral derivative calculation. But let's first try to derive what is Laplace transform of derivative. Let's assume we have a function ft and the derivative of this function is dft dt. Okay, we know the Laplace transform of the ft is Laplace transform ft by definition equals to the integral from 0 to infinity, and we have ft e minus st dt. Okay, and the s is sigma plus j omega. Okay, what we want to calculate now is the Laplace transform of derivative of ft, which is Laplace transform of f dot t, or we could just write Laplace transform of dft dt. Okay, so by definition, we just plug this df dt into the equation. What we get is 0 to infinity, and df dft dt e to minus st dt. Okay, and from here we can cancel the dt is cancelled. We can rearrange this equation like I will write here like 0 to infinity e to the minus st dft. Okay, so it just changes the order. I move the st to here, and then take the dft term, move to the back side. Okay, and this derivative looks very weird, but if we know the rules, we have a rules duv equals u dv minus v du. Okay, by use that in this equation, you can assume this is u and this is v. Okay, what we have here is u dv. This u dv equals, rearrange this, we got duv minus v du. Okay, so by using this derivative rules, and we can see this is equal 0 to infinity, same, and it's equals duv d u is e to the minus s e to the minus st. Let's rewrite, get this clear. D e to the minus st, and v is ft. Okay, minus v is ft, ft, and du, u is est, so it's d e minus st. Okay, and this is very straightforward. You have a derivative term here, then you integral, so you get this term back. So what you get here is very straightforward. E minus st ft 0 to infinity, and here it's 0 to infinity ft. We can take the de to the minus st, we can take e to minus st back, then dt here, but at the same time, after it gets the derivative e to minus st, you need to take care of the exponent term, so you got a minus s back. So it's, you take the minus s is constant, so we take that out, so this turns into plus s. Okay, then when this is infinity, this term is negative exponents, it's turning into a 0. And when this is 0, this term turning into a 1, then you get f0 back. So it's f0. And here we can rearrange this term. We can rearrange this term like s, just copy it down here, 0 ft e to the minus st dt. Okay, Now this is very clear now. So what is this term? By definition, that's the Laplace transform of ft. Okay, so what we get here is e0 to the minus f0 plus s, the Laplace transform of ft. Okay, and if we look back in the beginning, we have here, and that's the results. You can write this down. So the Laplace transform of dft dt is equals to the s times the Laplace transform of the ft, the ft function, and minus some constant. Okay, so what we see here is the Laplace transform derivative is just simply the Laplace factor s times the Laplace transform of the original function. So you take care of the derivative. Just you turn the derivative into a very simple multiplication here. Okay, so that's the whole point of this Laplace transform. And what's the application in electronics? Let's say take for example a capacitor. We know the capacitor, the current of the capacitor equals C dV dt. Okay, this is the current of the capacitor, so it's proportional to C, and the derivative of the voltage change is voltage. And if we look this in Laplace format, so we got the Laplace transform the current times a constant, and we can turn this derivative into with this equation to the Laplace format. So we get CS V, we use capital V, S. Okay, so we get rid of the derivative, just add a S in front of it, and take the Laplace transform of the V. That's the format here. And what we get here, if we rearrange this term, we write V S divided by IS. So the voltage, Laplace transform of voltage divided by the current, which equals 1 over CS. Now you turn this very complicated derivative into a very straightforward Ohm's law. So basically, normally when S, we know S equals sigma plus j omega. For steady state, sigma is equals 0, so S equals j omega. So what you get here, you plug in, you got 1 over j omega c. So that's basically the impedance format of the capacitor. Okay. Similar, you can derive the equation for a inductor, for example. We know the inductor derivative form of the inductor is V equal L di dt. Okay. The voltage equals the inductance times the current derivative. Okay, then if we take the derivative format Vs, we use capital V for the Laplace transform, times L, the inductance, and this derivative turn into a S times the current of Laplace transform. And rearrange, we divide Is over here, we get V S divided by IS equals LS. Okay, S is j omega in this case, so as we have j omega L. Let's correct here, j omega L. Well, omega is angular frequency, you can write 2 pi f j L. Okay, once you convert this capacitor or inductor into a impedance format, this impedance is dependent on the frequency. So then you can just simply use the Ohm's law to do the calculation, and you need to get the TDS derivative or integral.